So in this video, we will discuss problem number 6 from the 2021 AP Calc AB exam. It's a non-calculator question that deals with differential equations, and there is a little bit of a context to it here. So they tell us that we've got a patient that receives some medicine, and then the amount of medicine in milligrams that are in the patient after t hours will be modeled by the function y equals a of t. And we have the differential equation for y equals a of t. So the derivative dy dt would be equal to the fraction that you see here. Did I cover up part of the problem statement here? It seems like I have. Let's see if I can fix that. So I just kind of dragged the problem statement up a little bit so that the screenshot I placed over top of it is no longer covering it up. So the end of the problem statement there is telling us that at t equals 0, we've got 0 milligrams of medicine in the patient. In part A, they give us a slope field, and they ask us to sketch a solution curve through the point 0, 0. So you're going to start at 0, 0 and just use the line segments that you see within the slope field as a guide to draw your curve. What you would not want to have happen in a situation like this, you notice I've leveled off at this horizontal portion of the slope field. What we definitely can't have happen is something like this, right? If I cross that horizontal portion of the slope field, the slope of that little stretch of the graph I just inserted is not met by that horizontal segment that I'm crossing there. So the graph should look something like this without what I just added. Part B tells us that we want to interpret, or asks us to interpret, this limit. So the limit as t approaches infinity of this function a of t, and keep in mind a of t represents the amount of milligrams of a medication in a patient after t hours. So as t approaches infinity, the amount is going to be approaching 12. And so what that basically means is over time, there's always going to be an equilibrium level of 12 milligrams of this medicine within this patient. And I've stated that here, right? So I made sure that I used hours, right? Time is approaching infinitely many hours, and we're going to have 12 milligrams of the medication left in the patient's bloodstream after time plays out infinitely. Part C is the big part of this one. So you're asked to use separation of variables to find the particular solution to the differential equation. So when you separate your variables, you're going to want to divide the dy by 12 minus y. I left the 1/3 over on the right-hand side and just multiplied across the dt. I needed to do the antiderivative of both sides here. You have to watch out. The left-hand side does require a u substitution. If you don't think about that, what you miss is this negative that arises because of it. So I want to find a specific solution. The fact that it says y equals a of t implies that we're going to have to solve this equation for y. So I went ahead and I solved my equation for y. I've gone through a little sequence here that you've probably used yourself a few times if you solved enough differential equations. So I want to find a way to get rid of the absolute values. And over here, what I have is I have e to negative 1/3 t plus c. Well, if I rewrite that as e to the negative 1/3 t times e to the c, multiplication of like bases, and then I re-represent e to the c as an arbitrary constant a, I give the right-hand side of the equation a way to become negative by replacing e to the c with an arbitrary constant a. I can therefore allow the left-hand side of the equation to become negative as well and drop those absolute values. And then to solve this for y, I added the y to the right, subtracted e to the negative 1/3 t from the left, and had my general solution, but I wanted a specific solution. So I have this ordered pair. When time is 0, the amount of medication is 0 milligrams. So I put 0 in for t, I put 0 in for a. I did something bad here. I'm going to have to adjust this, and we'll resume this discussion. Give me 1 second. So I caught the fact that I used a variable, or I guess a constant, a letter to represent a constant in this position that was already being used within this problem. I'm so used to using a in a position like that I just kind of did it by default, but I am not able to here because a is actually already defined as something different within this problem. So that's why I paused things and made that adjustment. I initially changed the A's to capital B's, but then if you look ahead at the last part of this, they've also used capital B. So A little bit of a fiasco there trying to get it to be notationally correct, but I've got a letter that I now am able to use to represent that constant, and when I plug 0 in for t and 0 in for y, or for a, this a, not the a that I was talking about 30 seconds ago, I should be able to solve that for that constant, and that gives me 12. And so here would be my specific solution in the lower right-hand corner of the screen. And then the final part of this says that we've got a different patient that has a different procedure used to administer the medication. And the amount of medication within the second patient after t hours is going to be modeled by the function b of t. B of t satisfies this differential equation, so different than the one that we've dealt with throughout the problem so far. They tell us that at the 1 hour mark, we've got 2.5 milligrams of medication in the person. And then it asks, is the rate of change of the amount of medication in the second patient increasing or decreasing at time 1? So they say, is the rate increasing or decreasing? And hopefully what that triggers for you is the fact that you're going to have to look at a second derivative. The rate of change of a rate of change would have to be analyzed in order to make a judgment about whether the rate of change itself is going up or going down. And so when you take the second derivative here, you're just going to take the derivative of the left-hand side with respect to t. When you take the derivative of the 3, it goes away. I'm going to have to copy that subtraction, that negative, in as the coefficient of this fraction. And when I take the derivative of that fraction, I'm going to have to do that derivative implicitly, and I'm going to have to use a quotient rule. So I've got the function from down low times the derivative of what's up high, minus the function that's up high times the derivative of what's down low, square the original denominator. I need to know what's going on with this second derivative at the 1 hour mark. Well, at the 1 hour mark, we've got 2.5 milligrams of medication within the person. I am therefore able to put 1 in place of my t's. So you see that happening here. Missed it, but close enough, in there. And I also am going to be able to put 2.5, or 5/2, in place of the y. Now, the one thing that's going to be a little more work to determine is what's the value of dy dt at this same spot. Well, the value of dy dt at that same spot, if you evaluate the first derivative at 1 comma 2.5, what you end up with is this difference here, which simplifies to 13/6. I didn't really simplify any further because I looked at this. Okay, so the issue that I had, and the reason why I had to kind of analyze this a little further, my notation was not great. When I looked at this prior to sitting down to record this discussion, uh, I looked at this as the sign of that first term in the numerator, but that's not the case. That's a negative out in front of the fraction. So just my shoddy notation here caused me to, I guess, run the risk of not having the right sign for my second derivative. So I did do a little bit of simplification. This is 3. If I multiply 3 times 13, I get 39/6. Well, that's going to be over 6. If I have something to over 6 minus 2.5, my numerator is positive. So if I've got a positive divided by a positive, but the overall fraction's negative, I am less than 0. So the reason why I wanted to make sure I was correct here was because I should be distributing that negative into both terms within the numerator, and that could have caused my second derivative to have a different sign than I had initially thought, just due to the placement of that negative essentially is what caused me to get a little concerned whenever I was talking a few minutes ago. But we are okay. The second derivative is negative when we evaluate it at 1 comma 2.5. And because the second derivative is negative, we know that the rate of change of the amount of medication in this patient's bloodstream is decreasing.